And welcome to 14-4, the mixtures and movements of gases. In this particular podcast, we're going to take a look at some of the properties of mixtures of gases, particularly the pressures. And then we're going to also discuss the movements of gases, whether it's just in the ambient air or whether it's inside of a container. All right. The first thing we want to take a look at is a mixture of gases and the pressures that those gases in the mixture exert. The partial pressure, which is the first definition that we want to tackle, is simply the pressure exerted by a gas in a mixture of gases is the pressure exerted by a gas in a mixture of gases, and it will behave or exert the pressure as if it was the only gas in the container. As if it were the only gas in the container. All right, so let's go ahead and scroll down, take a look at individual gases and the mixture of gases. And if we look at letter A, all right, in the lime green there, if it's in a container, a particular container at a particular pressure, or I'm sorry, at a particular temperature, it's going to exert a pressure of 100 kilopascals. So when you put it in a mixture of gases in the exact same size container and temperature, etc., it is going to exert a partial pressure of 100 kilopascals. It does not change when you put it with other gases. Similarly, if you take a look at letter B exerts a pressure of 250 kilopascals in this container at this temperature. When you put other gases with it into a mixture, it is still going to exert the exact same pressure. And you can imagine when we do letter C here, you're going to find the exact same thing. Letter C in blue gives a pressure or exerts a pressure of 200 kilopascals. So when you put it in the mixture, it still exerts a pressure of 200 kilopascals. The only difference between pressure and partial pressure is simply the partial pressure is when it is in a mixture of gases. That's it. But you treat each individual component of that mixture as if it were by itself. Now, if you notice, the total pressure is the sum of all the individual components. So you add them up, you get 550 kilopascals. That is Dalton's law of partial pressures. Dalton's law of partial pressure simply says that the total pressure of a mixture of gases is equal to the sum of the partial pressures of each component. All right, so you just add up all the partial pressures of all the individual gases in the mixtures, and voila, you have the total pressure. So what you can do is you can measure the total pressure. If you know various pressures of other gases, you can solve for a pressure of a unknown gas. For example, let's change this to, let's go with orange, since we're not using orange right now. Let's say that we measure a total pressure of 800 atmospheres. All right. And you have, now we're not using these values here, let's go ahead and cross those out. Let's say letter A gives a partial pressure of, let's say, 150 atmospheres. Let's say letter B gives a pressure of 300 atmospheres. What would the pressure of gas C be in that mixture? Well, you know that the sum of all of the pressures is going to have to equal 800 atmospheres. So 300 plus 150 together, that's going to be 450. And so if the total has to be 800, if you subtract 450 from 800, that gives you 350 atmospheres for that last component. Right? So that's what you're dealing with when you're dealing with partial pressures. They behave as if they're by themselves. The total pressure is just adding up all the individual partial pressures. Now, scrolling down. If we take a look at gas movement is really summarized in two different laws, Graham's law of diffusion or Graham's law of effusion. Now the difference, diffusion is the movement of gases in the ambient air. Okay? If you take a look at the definition in the textbook, it says that it's the tendency of molecules to move toward areas of lower concentration until the concentration is uniform throughout. Basically what this means is that gases spread out. Okay? And it spreads out in a container, it spreads out in the room, whatever the case may be. Effusion, on the other hand, is the movement of a gas through a pinhole in a container into an evacuated container. All right. Now, the reason why we talk about in terms of diffusion and diffusion is very complex, because if you have a person standing right here and another person standing right here, let's just say that this person is wearing way too much cologne, so that smell is really coming off it. In order for the smell to travel from this person over to this person, this gas particle has to move its way through literally trillions upon trillions upon trillions of particles before it gets to this next person. And so it's going to bounce all over the place as it moves its way through. And this movement is very complex and random and is difficult to model. On the other hand, when you're dealing with effusion is simply having a chamber with a little tiny pinhole in it. And so say this chamber here is filled with gases. Effusion is how fast the gas can make its way through that pinhole. Well, the reason why this is much easier is because there's nothing in this other chamber to block it. The only thing that determines how fast it's going to be moving through there is how fast these particles are moving. And so diffusion and infusion is basically talking about how fast these molecules are bouncing around and moving around. And so you have a take-home message. Gases of lighter molar masses or smaller molar masses are going to effuse or diffuse faster than gases of higher molar masses. The smaller the molecule is, the faster it moves. The faster it moves, the faster it's going to be able to effuse or diffuse through a container or throughout a room. All right? Okay. So all you have to be able to tell us from this chapter, or from this section anyway, is the idea of partial pressures and how to calculate those, and the idea of diffusion and effusion. The smaller the particle is, the faster it moves. Let me give you a quick little example here, and then we'll wrap this thing up. If you have two molecules, hydrogen and oxygen, which one is faster at the same temperature? Well, hydrogen weighs 2.016, oxygen weighs 32.00 grams per mole, so therefore the hydrogen will be faster than the oxygen. On the flip side, you could say that the oxygen would be slower. All right? That concludes Chapter 14.